everyone, welcome to another deep dive. Are you ready to explore the history of astronomy?
Absolutely. It's a pretty amazing journey.
It really is, from like the earliest stargazers, trying to make sense of the night sky to like today with black holes and string theory. It's incredible.
It really is remarkable how far we've come in our understanding of the cosmos.
So for this deep dive, we're using David Linton's book, Eudoxus to Einstein, A History of Astronomy. We're going to trace the evolution of astronomical thought, all those aha moments.
It's like a detective story, uncovering the secrets of the universe one discovery at a time.
I like that, a cosmic detective story. So let's rewind back, way back to like ancient times.
Okay.
Imagine you're like an ancient Babylonian. You're looking up at the sky. What's important to you?
Well, for them, it was less about why things were happening in the sky and more about when.
When?
They were incredible at predicting celestial events.
Okay, so like eclipses, stuff like that.
Exactly. Eclipses, planetary movements, you name it.
Yeah.
They needed that knowledge for their calendars and for their religious practice.
Optical astronomy.
Very much so. And they made a lasting contribution. They were among the first to use a system of longitude and latitude.
Like we use on maps.
Exactly.
Yeah.
Except they used it to map the stars, the planets, along what we call the ecliptic.
The ecliptic, that's the path the sun seems to follow, right?
Exactly. So they created this coordinate system, and it's actually something we still use today, in a way.
Wow. So the Babylonians set the stage with their observations and predictions, and then the ancient Greeks came along, and they kind of took things in a different direction, right?
They did. The Greeks were obsessed with geometry.
Everything had to fit into their perfect little models.
In a way, yes.
Yeah.
They wanted a model, something visual, that could explain those movements that the Babylonians had been tracking.
And that's where Eudoxus comes in, right? With his system of, what were they, concentric spheres?
Yes, concentric spheres. Imagine like a series of nested spheres all centered on the Earth.
Okay, like one of those, what are they called, Russian nesting dolls?
Kind of. And each sphere carried a celestial body. So you've got
Sure.
the sun, the moon, the planets, even the stars, all attached to these rotating spheres.
And by adjusting the axes and the speeds of these spheres, he could explain, at least roughly, how things moved in the sky.
It was an ingenious idea for his time.
It really was, although it wasn't perfect, right?
No, it wasn't. It had its limitations.
Yeah.
The Greeks, you see, they were limited by this idea that celestial motion had to be based on perfect circles.
Ah, yes. The perfect circle. It seems like kind of a roadblock looking back.
It would certainly cause some issues later on as observations became more precise.
So how do they deal with that?
Well, that's where another brilliant Greek astronomer comes in, Hipparchus.
Hipparchus, he was like the data king, right? Didn't he make some of the most accurate measurements of his time?
He did. He was meticulous. He actually used trigonometry, which he helped to develop.
Trigonometry. I remember struggling with that in school.
Well, Hipparchus used it to make these incredibly precise measurements of the sun's position. And he noticed something interesting.
What was that?
He noticed that the sun's speed across the sky wasn't constant.
It didn't just move smoothly.
It didn't. It seemed to speed up and slow down at different points in the year.
Okay, interesting. So how did he explain that? Did he ditch the whole perfect circle idea?
He didn't, not completely. He came up with a clever workaround. He introduced the concept of the eccentric circle.
What?
The eccentric circle. Basically, he said that Earth wasn't exactly at the center of the sun's orbit. It was slightly off to the side.
Okay, so still a circle, but a little off kilter.
Exactly. And, that seemingly small adjustment was huge. It was a step toward the idea of elliptical orbits.
Which we know now is how planets actually move.
We do, but it would take some time and another brilliant mind to fully unravel that mystery.
So we've got Hipparchus, right? Challenging that whole perfect circle idea.
He nudged things in the right direction, but it was Ptolemy who really took those ideas and ran with them.
Ptolemy. Now, he wrote this book, Almagest.
Yeah, it was like the astronomical Bible for like over 1,000 years.
Seriously.
It was hugely influential, synthesizing all this astronomical knowledge.
So Ptolemy, he was still on board with the Earth being the center of everything.
He was. His model was still geocentric.
But he had to make some tweaks, right? To explain those weird planetary movements.
He did. Remember how we talked about planets sometimes seeming to move backward?
Yeah, retrograde motion. It's like they back up for a bit.
Exactly. Well,
Yeah.
Ptolemy explained that with, get this, epicycles.
Epicycles.
Yeah, he said planets moved on these small circles, these epicycles, while the center of that epicycle, it moved along a larger circle called a deferent.
So it's like a circle moving on another circle.
Exactly. It sounds complicated, but it actually worked really well to predict where planets would be.
Ingenious. Well, kind of. But it also seems, I don't know, a little clunky.
You're not wrong. And Ptolemy had to make even more adjustments. He introduced the equant. It was this point, not the Earth, that the planets orbited around at a uniform speed.
So not exactly keeping things simple, was he?
It was a compromise, and it kind of went against that Greek ideal of uniform circular motion.
But his model worked. It was accurate.
It was, and it was embraced for centuries, especially by Islamic scholars who made their own significant contributions to astronomy.
It's amazing to think how knowledge traveled and evolved across different cultures.
Absolutely. Figures like Al-Farghani, he simplified Ptolemy's work so it could reach a wider audience.
Kind of like the astronomy for dummies of his time.
You could say that.
Yeah.
But other Islamic astronomers, they went beyond just preserving knowledge. They challenged it.
Oh, really? Like who?
Well, there was Thabit ibn Qurra, for example. He questioned Ptolemy's idea about the wobble of Earth's axis, the precession.
You mean like how Earth kind of spins like a top?
Exactly. Ptolemy thought that wobble was fixed, but Thabit ibn Qurra, he suggested it might actually vary over time.
That's pretty radical for that time to question Ptolemy like that.
It was. And then you have someone like Al-Biruni. He used spherical trigonometry to solve a very practical problem.
Trigonometry again.
It was essential for figuring out the direction to Mecca for prayer, the Qibla.
Wow, so astronomy being used for religious purposes.
It was intertwined with many aspects of life.
Mm-hmm.
But getting back to your earlier point about Ptolemy's model being a bit clunky,
Yeah.
well, some astronomers tried to come up with different systems altogether.
Oh, tell me more about that.
One name that comes to mind is Albit.Rugel. He developed a model based on concentric spheres, kind of like Eudoxus centuries earlier.
Trying to get back to those perfect circles.
It was a valiant effort, but ultimately, his model just couldn't match the accuracy of Ptolemy's.
So Ptolemy's model, for all its complexities, it held up.
For a while, yes. But there was this growing sense that maybe, just maybe, there was a different way to understand how the universe was structured.
A universe that wasn't centered around Earth.
Exactly. And that leads us to a pivotal figure, Nicholas Copernicus.
Copernicus, man, what a revolutionary. He said, nope, the Earth is not the center, it's the sun. Like, that's a huge shift.
It was a big shift, but Copernicus, he wasn't completely breaking from the past. He still held on to some of those old ideas.
Like what? You mean he was still using epicycles?
Yeah, he was. Even though he put the sun in the center, he still used epicycles to, like, fine-tune the planet's orbits.
It's like he couldn't quite let go of those perfect circles.
Old habits die hard,
Yeah.
right? But even though it wasn't a complete revolution, his model, it had huge implications.
Yeah, putting the sun at the center, it simplified things, and it really changed how we saw ourselves, like our place in it all.
It was a huge philosophical shift, too.
It makes you wonder, what would those early astronomers think if they could, like, fast forward to today and see what we know now? But, okay, back to the story. We've got to talk about Tycho Brahe. Now, he was, like, obsessed with making accurate observations.
Tycho was incredible. He built his own observatory, had the most amazing instruments.
He was all about the data.
Absolutely. He made the most precise measurements of the planets that anyone had ever made up to that point.
Okay, so he's got all this data, but here's the thing. He didn't completely buy into Copernicus's idea.
He didn't. He actually came up with this kind of hybrid model.
Grid.
Yeah, like a compromise. So the sun orbited the Earth, but all the other planets, they orbited the sun.
That's like, I'm not ready to give up the Earth-centered universe completely.
Right, and it just goes to show that even the greatest minds, they struggle with new ideas.
Totally. But even though Tycho wasn't, like, fully on board with the heliocentric model, his data, it turned out to be really, really important.
It was. Because that data, it fell into the hands of his assistant, Johannes Kepler.
Kepler. Now, this guy, he was not afraid to break the mold. He's the one who finally ditched those pesky circles.
He did. Kepler, he took Tycho's data, and he spent years working with it, trying to figure it all out.
Years. That's dedication.
And finally, he realized that the planets, they weren't moving in perfect circles after all. They were moving in ellipses.
Ellipses? Okay, so like ovals, with the sun at one of the what are they called? The focus point.
Exactly. That was a huge deal. It was such a departure from what everyone had always believed.
It's like the universe just got a whole lot more interesting. And he didn't stop there, did he? Didn't he figure out something about the speed of planets, too?
He did. He discovered that a planet's speed changes as it orbits the sun.
So it's not like a steady cruise around the sun.
Nope. It speeds up when it's closer to the sun and slows down when it's farther away.
Makes sense. More gravity, more speed.
Exactly.
Yeah.
And that's actually his second law of planetary motion. A line between a planet and the sun, it sweeps out equal areas in equal times.
Okay, you lost me a little bit there, but basically the planets are speeding up and slowing down in a predictable way.
Yes. And then there's his third law, which this one might make your head spin a little bit.
Hit me.
It connects a planet's orbital period, how long it takes to go around the sun, with its average distance from the sun.
Okay, so, like, planets farther away, they take longer to orbit.
Exactly. But he figured out the exact mathematical relationship. The square of the orbital period, it's proportional to the cube of the average distance.
Whoa, okay. Math. But the point is, he found these elegant laws that described how the planets moved.
He did, and these laws, they worked beautifully. But there was still this question, why? Why were the planets moving like this?
That's where good old Galileo comes in, with his telescope.
Galileo, he changed everything with his observations. He saw things no one had ever seen before,
Like what?
like the phases of Venus.
Venus has phases, like the moon.
Exactly, just like the moon. And the only way to explain that, to explain those phases, was if Venus was orbiting the sun.
So another nail in the coffin for the Earth-centered universe.
It was. And then there were the moons of Jupiter.
Wait, Jupiter has moons, more than one?
More than one. He discovered 4 of them orbiting Jupiter.
So that blows the whole everything revolves around the Earth idea right out of the water.
It was huge. It showed that there were other centers of motion in the universe. The Earth wasn't so special after all.
Mind-blowing. So we've got Copernicus changing the perspective, Tycho gathering incredible data, Kepler finding those amazing laws of planetary motion, and Galileo providing the observational proof. It's like it all built on itself.
It did. And it was the perfect setup for perhaps the biggest giant in the history of physics, Isaac Newton.
Newton, he's the one who put it all together, right? He
Yeah.
finally explained the why.
He did. With one simple, elegant law, the law of universal gravitation.
Which says what, exactly, in, like, plain English?
It says that every object in the universe attracts every other object.
Everything. Like me and my coffee cup.
Yes, even you and your coffee cup.
Yeah.
But the strength of that attraction, it depends on 2 things. How massive the objects are and the distance between them.
So the bigger and closer things are, the stronger the attraction.
You got it. And that one law, it could explain so much. Why planets orbit the sun in ellipses, why things fall to the Earth, even why we have tides.
It's like he revealed the secret code of the universe. But even Newton's law, it wasn't the end of the story, was it?
Nope. There were still some mysteries. For one, Newton's law worked great for like 2 objects, but when you get 3 or more objects interacting, things get really complicated really fast.
Okay, so like the Earth and the sun, no problem. But throw the moon in there and suddenly it's a free-for-all.
It's called the n-body problem. And it made predicting the long-term stability of the solar system a real challenge, even for Newton.
The universe, always keeping us on our toes. And then there's that whole thing with Mercury, wasn't there? That little troublemaker.
Ah, yes, Mercury. It has this weird wobble in its orbit that Newton's theory just couldn't explain.
A wobble.
Yeah, its orbit, it doesn't stay in place. It kind of like shifts a little bit each time Mercury goes around the sun.
So Newton's theory, for all its brilliance, it couldn't explain everything.
It couldn't. And that little anomaly in Mercury's orbit, it was a clue, a hint, that there was more to gravity than even Newton had imagined.
And that's where Einstein enters the picture, right? With his mind-blowing theories of relativity. It's like the universe went from a nice orderly clockwork to something completely different.
It did. Einstein's theory completely changed our understanding of gravity, space, and time. But you know what? I think we'll have to save that for another deep dive.
Yeah, we've covered a lot of ground already, from ancient stargazers to Newton and Einstein. It's amazing to think about how far we've come in our understanding of the cosmos.
It is, and the journey's not over yet. Who knows what incredible discoveries await us in the future?
That's the exciting part. So until next time, keep looking up, keep asking questions, and never stop exploring the wonders of the universe. Thanks for joining us for this deep dive into the history of astronomy.